Today we're going to be looking at 3D molecular modeling design, the synaptic cleft, and the synapse construction. What we have at the moment is two neurons stuck together. So we're looking at the presynaptic neuron and the postsynaptic neuron. The presynaptic neuron is where the signal is coming from, and we want to transfer that signal through the synaptic cleft and into the postsynaptic neuron. To help us understand kind of what we're looking at again, we want to see these are sodium gated channels using a ball and chain mechanism on both sides of this synapse. Sodium is the blue, potassium is purple. We have a vesicle inside with neurotransmitters, in our case acetylcholine, a calcium channel with calcium, which is white. These are snare proteins allowing us to be able to, which connects the vesicle into the membrane. We have reuptake proteins, acetylcholinesterase, and acetylcholine receptor. Again, sodium channels, potassium being green. For more information or to review how an action potential works, please see a different video. But for our purposes, we're going to look at how the signal is transferred from the presynaptic neuron to the postsynaptic neuron. To do that, imagine an action potential coming through the presynaptic neuron, causing the sodium channels to open, allowing the sodium to enter, which then depolarizes our cell. As soon as the depolarization reaches peak, just as if the potassium channels open, the calcium channels will also open. This allows a flood of calcium in. The calcium channels only exist at the terminal end of the axon. So there's a very end down here where the cleft is. The calcium entering binds to this membrane protein. Okay, that membrane protein causes a chain reaction, causing the snare proteins to bind together and the vesicle to move towards the end of the membrane. The membrane's endocytose, the cell endocytoses acetylcholine out by the binding of the snare proteins, causing acetylcholine to flood into this synaptic cleft membrane. This allows it to bind to the acetylcholine receptor. The binding of acetylcholine to the acetylcholine receptor causes that receptor to open, and again causing the flood of sodium to come through. This causes the postsynaptic membrane to reach threshold, allowing the sodium channels to open on the postsynaptic side, again causing more sodium to enter, and a depolarization of the cell, and ultimately the continuation of the action potential. So this acetylcholine would be referred to as an excitatory neurotransmitter, meaning it keeps the signal going versus an inhibitory one. To stop the acetylcholine, this reaction really quickly, a few different things can happen. One, acetylcholinesterase is an enzyme that very quickly starts to degrade acetylcholine. This prevents the signal from continuing. Some of the acetylcholine can be reuptaken through endocytosis into the cell, and others of it can quickly be taken up through these uptake transport proteins and reassembled back inside the neurotransmitter. All of this very quickly causes the signal to stop and closes the sodium gates, ultimately allowing the signal to continue, but to stop the signal from continuing across the synaptic cleft.